Okay, we can use equations with two variables to represent relationships between two quantities. For the most part, we're going to use the variables x and y. So we can represent the relationship between x and y. In this case, we can say y is equal to 4x, which is to say that y is 4 times larger than whatever x is, or 4 times greater than whatever x is. So this is an equation with two variables, x and y. To check solutions to this equation, we're going to need to plug in and make sure that the equality is maintained. So let's check to see if 3 and 10 are solutions to this equation. Notice, by the way, that solutions for equations with two variables are going to come in the form of ordered pairs like this. Okay, 3 and 10 is an ordered pair that we might graph 3 on the x-axis, 10 on the y-axis. And also remember that in this case, 3 does represent the x value, and 10 represents the y value. So we're going to plug in and see if this is a solution. So instead of y, I'm going to write 10 equals 4 times 3. Notice I'm maintaining that pattern of when I plug in for a variable, I use parentheses around that number. Then I can simplify. 10 equals 4 times 3 is 12. Is that true? No. So 310 is not a solution to y equals 4x. And that's how you can check to see if any given point is a solution to an equation with two variables. We may be asked to represent a given situation with a table, a graph, and an equation. Here's a situation we talked about previously in class. This idea that there are tickets to a museum that cost $4.50 a piece. And I'm going to go through and just show you what we mean by representing it in a table, a graph, and an equation. Here's the start of our table. So to fill in our table, we want to see what we're talking about. And what we're talking about in this case, we're going to be representing the total cost based on the number of tickets given this situation. So we can start filling in our table pretty simply. If there is one ticket, the total cost is $4.50. If there are two tickets, the total cost is $9. If there are 3 tickets, the total cost is $13.50. If there are 4 tickets, the total cost is $18. And if there are 5 tickets, the total cost is $22.50. So there we have a table representing this situation. And that's all they mean by a table, something as simple as that. Now the next thing they ask us to do is do an equation. And we actually did this in class. Remember, we looked at this and we said, okay, tickets to the museum cost $4.50 a piece. I think the word in class we used was each. And we knew that sort of meant multiplication. So we came up with this equation. 450, or 4.5 in our terms, n is equal to total cost. Remember, I represented total cost like a T sub C. So total cost, and there's our equation right there. So now we've done equation and table. Let's talk about doing a graph. So here's our graph. And basically we want to plot the points where these things sort of come out even. Now the issue here is, you'll notice our y-axis is probably not big enough because it only goes up to 6, and we know after 2 tickets we're already going to be at $9. So let's assume our y-axis is in tens, 10, 20, 30, 40, 50, 60 instead of 1, 2, 3, 4, 5, 6. And if that's the case, it's going to be a little bit of an estimation to put the points on there, but we'll get the idea. So I'm going to go to where it's 2 and 9, because after 2 tickets we know we have $9 total, which is going to be right there, right before 10. After 4 tickets, we know it's 18, which is a little bit further before 20. Right there. Oh, I made a mistake. The mistake I made is I put it at 3 when we were talking about after 4 tickets. After 4 tickets, it's right there. Good. And then after 5 tickets, $22.50. After 6 tickets, $27. which is just under 30, but a little more under than 18 was under 20, and so on and so forth. So you can get an idea of what a graph of this would look like. Here's our line. Of course, that line doesn't really represent it. And there we have a line that represents our information. So we've done a graph, we've done a table, and we've done an equation. Those are three ways of representing a two-variable equation, as we had in this case with n and tc, or as we had on our first slide with y and x. I also want to talk about inductive reasoning. Inductive reasoning is the process by which we find a conclusion based on a pattern. So it's not based on outside information or something else that we know from the past. It's just based on a pattern that we're seeing happen over and over again. Let me show you an example. Here we have the beginning of a sequence of numbers, 1, 3, 5. Let's take a swing at what we think might come next. I would say 7, 9, 11. I'm saying that because I'm seeing a pattern develop. It seems like I'm listing every odd number. So based on inductive reasoning, or by looking at the pattern, I'm suggesting that the next numbers would be 7, 9, and 11. That's inductive reasoning. Here's another example of a pattern. I'm going to use inductive reasoning and see if I can draw basically what I think the next shape would be. So I think it would have a base of 5 and then 5 going up the sides in a pyramid structure like this, because that seems to be the pattern following all along. I'm using inductive reasoning, following the pattern to figure out what that next one is, and I could keep doing that for the series. So that's inductive reasoning.